What if I told you that gravity, the force you think is pulling you down right now, doesn't actually exist? Not in the way you've been taught your entire life. Right now, as you sit there watching this video, you're not being pulled toward the earth. You're being pushed. The ground beneath you is accelerating upward into your body at 9.8 meters per second squared, and you can't even feel it happening. Your entire understanding of the universe has been built on a beautiful lie. And in the next 3.5 hours, I'm going to completely dismantle everything you thought you knew about the force that holds galaxies together and makes apples fall from trees. Here's the kicker that's going to haunt you. Gravity isn't a force at all. It's a consequence of the shape of reality itself. The universe is curved, bent, twisted by the presence of mass and energy. And what we call gravity is simply objects following the straightest possible path through warped spacetime. You're not falling toward Earth right now. You're trying to move in a straight line through time. And the curved geometry of spacetime around our planet is what creates the sensation you call weight. Einstein figured this out over a century ago, and yet we still teach children that gravity is some mysterious force that pulls things together. We lie to them because the truth is too strange to comprehend without the proper foundation. But here's what will absolutely blow your mind. The implications of gravity being geometry, rather than force, mean that the future is already written. If gravity is just the curvature of spacetime, and objects follow predetermined paths through that curvature, then your trajectory through the universe was set at the Big Bang. Every decision you think you're making, every movement you believe is voluntary. It's all just you following the geodesic path through spacetime that was carved out 13.8 billion years ago. Free will might be an illusion created by creatures too small to see the shape of spacetime. Before we go further, smash that like button and subscribe, because we're about to take a journey that will fundamentally alter how you perceive reality. Drop a comment telling me what country you're watching from and what time it is where you are. Want to see how gravity is affecting people across the entire planet simultaneously? And trust me, by the end of this video, that simple question will mean something completely different to you. Now, let's start with what you think you know, and I'll show you exactly where the cracks begin to appear. You learned in school that Isaac Newton discovered gravity in 1687 when he saw an apple fall from a tree. That story is mostly myth, but Newton's insight was revolutionary. He realized that the same force pulling the apple downward was also keeping the moon in orbit around Earth. This was the first time in human history that someone connected celestial mechanics with everyday experience. Newton's universal law of gravitation stated that every object with mass attracts every other object with mass, with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. The equation is simple: F equals g meod squared. This formula worked perfectly for over 200 years. But here's the first crack in the foundation. Newton himself knew there was something deeply wrong with his own theory. He couldn't explain how gravity worked. How does the sun reach across 93 million miles of empty space to hold Earth in orbit? What is the mechanism of transmission? Newton called it action at a distance. And in his own writings, he admitted that the idea of one object affecting another across empty space is to me so great an absurdity that I believe no man who has in philosophical matters a competent faculty of thinking can ever fall into it. The man who discovered the law of gravity didn't believe gravity could actually work the way his equations described. Think of it like this. Imagine you're playing pool and you hit the cue ball into the 8 ball. The 8 ball moves because the cue ball physically contacted it. You can see and understand the mechanism of transmission. But now imagine hitting the cue ball, and the 8 ball on the other side of the table starts moving without the cue ball ever touching it. That's essentially what Newton's gravity requires us to believe. The sun and Earth never touch, yet somehow the sun's mass reaches across the void and dictates Earth's motion. For 2 centuries, physicists used Newton's equations because they worked beautifully for predictions. but nobody could explain the mechanism. Enter Albert Einstein in 1915 with his general theory of relativity. Einstein's insight was so profound that it's still difficult to fully grasp even today. Gravity isn't a force at all. Mass and energy curve the fabric of spacetime itself, and objects simply follow the straightest possible paths through that curved geometry. The sun doesn't pull on Earth. The sun's enormous mass creates a depression in spacetime, and Earth is constantly falling into that depression while simultaneously moving forward, creating an orbital path. The moon doesn't orbit Earth because Earth's gravity reaches out and grabs it. The moon is moving in a straight line through curved spacetime. Here's what makes this absolutely mind-bending. Spacetime is a single unified thing. You can't separate space from time. When mass curves spacetime, it's curving your future just as much as it's curving the space around you. Every massive object in the universe is literally bending the shape of tomorrow. The sun isn't just curving the space around it, it's curving the flow of time. Time moves slower closer to massive objects. This isn't theory, it's measured fact. Clocks on GPS satellites have to be constantly adjusted because time moves faster in orbit than it does on Earth's surface. If we didn't account for Einstein's time dilation effects, your GPS would be off by miles within a single day. Let me give you an analogy that might help this click into place. Think of spacetime as a stretched rubber sheet. Now place a bowling ball in the center. That's the sun. The rubber sheet dips and curves around the bowling ball. If you roll a marble near the bowling ball, it doesn't travel in a straight line anymore. It curves around the depression created by the bowling ball. The marble isn't being pulled by some invisible force. It's simply following the curvature of the sheet. That's gravity. Now here's the twist that most analogies miss. Time is also part of that sheet. The depression doesn't just curve space. It curves the rate at which time passes. The marble rolls into the depression, partly because time itself is moving slower near the bowling ball, and objects naturally move toward regions where time passes slower. The experimental proof for this came from Arthur Eddington in 1919 during a total solar eclipse. Einstein's theory predicted that light from distant stars would bend as it passed near the sun because the sun's mass curves spacetime. During the eclipse, Eddington photographed stars near the sun's edge and compared their positions to where those same stars appeared at night when the sun wasn't in the way. The stars had shifted positions exactly as Einstein predicted. Light itself was following the curvature of spacetime. This observation made Einstein an overnight celebrity and revolutionized physics. But here's where things get really weird, and this is going to challenge everything you think about cause and effect. If gravity is just geometry, then there's no such thing as gravitational force propagating through space. When the sun pulls on Earth in Newton's model, there's a question of how fast that force travels. Does it move at the speed of light? Faster? Instantaneously? Einstein's answer is bizarre. The question is meaningless because there is no force. The sun isn't doing anything to Earth. The sun simply exists, and by existing, it curves spacetime around it. Earth follows the curvature. There's nothing being transmitted from sun to Earth because the curvature is already everywhere simultaneously. Except that's not quite right either, and this is where your brain really starts to hurt. If the sun suddenly vanished, just popped out of existence, Earth wouldn't immediately fly off in a straight line. The curvature of spacetime would ripple outward from where the sun used to be at exactly the speed of light. These ripples are called gravitational waves, and we detected them for the first time in 2015 when LIGO, Laser Interferometer Gravitational Wave Observatory, measured the spacetime distortions created by two black holes colliding 1.3 billion light-years away. The collision sent ripples through spacetime itself, and when those ripples passed through Earth, they stretched and compressed space by less than 1,000th the width of a proton. We built detectors sensitive enough to measure that. Think about what this means. Spacetime is a physical thing that can ripple, wave, and oscillate. Gravity isn't just a description of how objects move, it's a property of the stage on which everything exists. The universe itself is dynamic, flexible, capable of transmitting information through its own structure. When those black holes collided 1.3 billion years ago, they literally rang space-time like a bell, and we heard the echo in 2015. Now, here's your first major mind-blown moment. You are constantly creating gravitational waves. Every time you move your arm, you create microscopic ripples in space-time that propagate outward at the speed of light. Those ripples are unimaginably tiny, far too small to ever detect, but they're real. Your motion is permanently recorded in the structure of space-time, spreading outward forever. Every action you've ever taken has created gravitational waves that are still traveling through the universe right now, carrying information about what you did. In a very real sense, the universe remembers everything. What we're building toward here is a complete reconceptualization of what gravity actually is. And I promise you, by the time we're done, you'll never look at falling objects the same way again. But first, we need to go deeper into what mass actually is and why it curves space-time in the first place. Here's a question that seems simple, but opens up an abyss. Why does mass curve space-time? Einstein's field equations describe how mass and energy curve space-time, but they don't explain why this relationship exists. The equations are beautiful. G equals 8t. The left side describes the curvature of space-time. The right side describes the distribution of mass and energy. And the equal sign tells us they're intrinsically linked. But why? Why should the presence of matter distort the geometry of reality? The honest answer is that we don't know. We can describe the relationship mathematically with stunning precision. We can measure it experimentally. We can use it to predict everything from planetary orbits to the bending of light around galaxies. But the fundamental reason why mass curves space-time remains one of the deepest mysteries in physics. It's a brute fact about our universe: mass curves space-time, because that's what mass does in our universe. In a different universe with different laws, perhaps mass wouldn't curve space-time at all. But here's where it gets interesting. Mass and energy are equivalent. Einstein's famous E equals mc tells us that mass is just a very concentrated form of energy. That means energy also curves space-time. Light has no mass, but light carries energy, so light creates gravitational effects. The sun's light, streaming outward in all directions, is actually creating a tiny outward gravitational pressure. Powerful enough lasers could theoretically push objects using gravity rather than direct momentum transfer. This leads to one of the strangest implications. A box full of light weighs more than an empty box. Think of it like this. Imagine you have a perfect mirrored box, and you shine a laser inside, then seal it up so the light bounces around forever inside the box. That box is now slightly heavier than it was before, because the trapped light energy curves space-time. If you could measure precisely enough, you'd detect the gravitational field of the light itself. This has profound implications. Every time you turn on a flashlight, you're creating a gravitational field. It's unimaginably weak, but it's real. Now, let's talk about what happens when we push gravity to its absolute limits, because this is where the universe reveals its most terrifying secrets. Imagine compressing mass into a smaller and smaller space. As the density increases, the curvature of space-time becomes more extreme. Keep compressing. At some point, you reach a critical density where space-time curves so severely that not even light can escape. You've created a black hole. The boundary beyond which light cannot escape is called the event horizon, and it represents a one-way membrane in space-time. Cross the event horizon, and your future becomes unavoidably inside the black hole. All possible paths you can take through space-time lead inward. You can't escape not because something is pulling you in, but because the geometry of space-time itself offers no outward directions. It's like trying to go north from the North Pole. There is no north to go to. Carl Schwarzschild figured out the mathematics of black holes in 1916, just months after Einstein published general relativity, While Schwarzschild was serving on the Russian front during World War I, he solved Einstein's equations for the spacetime around a perfectly spherical mass compressed to a point. The solution showed that at a specific radius now called the Schwarzschild radius, something extraordinary happens. For Earth, the Schwarzschild radius is about 9 millimeters. If you could compress all of Earth's mass into a sphere smaller than a grape, it would become a black hole. For the Sun, it's about 3 kilometers. Here's what will blow your mind. We've actually photographed a black hole. In 2019, the Event Horizon Telescope, a network of radio telescopes spread across the entire planet, working together as one Earth-sized telescope, captured an image of the supermassive black hole at the center of the galaxy M87. The black hole itself is invisible, but we can see the glowing accretion disk of matter swirling around it, and we can see the shadow of the dark circle in the center where light cannot escape. That black hole has a mass of 6.5 billion suns compressed into a region smaller than our solar system. But here's the truly disturbing part. From the perspective of someone falling into a black hole, they cross the event horizon in finite time. From the perspective of someone watching from outside, the falling person appears to slow down as they approach the horizon, getting redder and dimmer, and they never actually cross. They appear frozen at the event horizon forever. Both perspectives are equally valid. This isn't an optical illusion. It's a fundamental consequence of time dilation. Time slows to a stop at the event horizon relative to distant observers. The person falling in experiences time normally, but from the outside perspective, they've been frozen in time forever. Think about the implications. If you fell into a black hole, from your perspective, you'd cross the horizon and hit the singularity at the center in seconds or minutes. But your friend watching from a safe distance would watch you slow down, freeze, and never actually fall in. They'd see you stuck at the horizon for the rest of the universe's existence. Both of you are experiencing reality correctly. Spacetime itself is structured such that both descriptions are true simultaneously. This is what happens when gravity becomes strong enough to significantly distort time. And here's the kicker. We still don't know what happens at the center of a black hole. Einstein's equations predict a singularity, a point where density becomes infinite and spacetime curvature becomes infinite. But infinity showing up in your physics equations usually means your theory is broken down. It means you're trying to describe something your theory isn't equipped to handle. We need a theory of quantum gravity to describe what really happens at the singularity, and we don't have that yet. The center of every black hole is a region where our best understanding of physics simply fails. Roger Penrose proved mathematically in 1965 that singularities must form inside black holes. They're not just artifacts of our simplified models. They're inevitable consequences of general relativity. He won the Nobel Prize in Physics in 2020 for this work. But what is a singularity really? Is it actually a point of infinite density, or does quantum mechanics intervene somehow to prevent the infinity? We don't know, and we can't know, because we can't see inside a black hole. Now here's a question that should keep you up at night. Could you be inside a black hole right now? Think about it. If you cross an event horizon, you don't notice anything special happening locally. Space isn't obviously curved in any direction you can point to. Time flows normally from your perspective. The only way you'd know you crossed an event horizon is by looking back and seeing that you can no longer receive signals from outside, and that all your possible future paths lead to the singularity. Some cosmologists have speculated that our entire observable universe might be the interior of a black hole. From inside, we can't tell the difference. The Big Bang singularity in our past and the event horizon at the cosmological boundary might be two aspects of the same structure. This is speculation, but it's grounded in serious physics. The mathematics allows for it. And that should be deeply unsettling, the possibility that our entire reality is playing out inside a structure from which escape is impossible. And at the end of time, everything will collapse into a singularity. Let me give you an analogy that captures the weirdness of black holes. Imagine you're in a rowboat on a river approaching a waterfall. Far from the waterfall, you can row upstream against the current. You have the option to escape. As you get closer, the current gets stronger. Eventually, you reach a point where the current is moving at exactly the speed you can row. This is like the photon sphere of a black hole light can orbit at this distance, but cannot escape. If you drift even slightly closer, the current exceeds your rowing speed, and you can no longer escape even by rowing at maximum speed upstream. You've crossed the event horizon. Beyond this point, all possible directions of rowing upstream, downstream, sideways still result in you going over the waterfall. The event horizon is the point of no return, not because something grabs you, but because the flow of spacetime itself is so strong that all paths lead inward. We're at about the 45-minute mark now, and if you're still with me, you're doing great. Hit that like button if your brain is starting to hurt in a good way, and leave a comment with the most mind-blowing thing you've learned so far. We're just getting started, and what comes next is going to make black holes seem simple by comparison. Let's talk about what gravity does at the largest scales imaginable, the scale of the entire universe. When Einstein first applied his general relativity equations to the universe as a whole, he encountered a problem. His equations predicted that the universe should be either expanding or contracting. It couldn't be static. But in 1917, everyone believed the universe was static and eternal. So Einstein added a term to his equations called the cosmological constant, essentially a repulsive form of gravity that could exactly balance the attractive gravity of matter and keep the universe static. He later called this his biggest blunder. Why? Because in 1929, Edwin Hubble made an observation that shook physics to its core. He discovered that distant galaxies are moving away from us, and the farther away they are, the faster they're receding. The universe is expanding. Space-time itself is stretching, carrying galaxies apart like raisins in rising bread dough. Einstein's original equations were right. The universe is dynamic, not static. Here's what this means. If the universe is expanding now, it must have been smaller in the past. Run the clock backward, and you reach a point where all the matter and energy in the universe was compressed into an infinitely small, infinitely dense point, the Big Bang singularity. Time itself began at the Big Bang. There is no before the Big Bang, because time is a property of the universe, and the universe didn't exist before the Big Bang. The question, what caused the Big Bang, may be meaningless because causation requires time, and time began at the Big Bang. Think of it like asking, what's north of the North Pole? The question has a grammatical structure that makes it seem valid, but it's actually nonsensical. You can't go north from the North Pole because north is defined as toward the North Pole. Similarly, you can't go before the Big Bang because before is defined in terms of time, and time started at the Big Bang. But here's where gravity becomes absolutely crucial. The expansion rate of the universe is slowing down over time due to gravity, right? Matter attracts matter, so the mutual gravitational attraction of everything in the universe should be gradually slowing the expansion, possibly eventually reversing it into a big crunch where everything collapses back together. That's what physicists expected. In 1998, two teams of astronomers, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, made measurements of distant supernova to determine exactly how much the expansion was slowing. Their results were so shocking that both teams initially thought they'd made an error. The expansion isn't slowing down, it's speeding up. The universe's expansion is accelerating. This discovery won the Nobel Prize in Physics in 2011 because it revealed something profound and disturbing. About 68% of the universe is made of something we call dark energy, and we have no idea what it is. Dark energy acts like Einstein's cosmological constant, a form of repulsive gravity or negative pressure that pushes spacetime apart, and it's winning. Dark energy is stronger than the attractive gravity of all the matter in the universe. and it's causing spacetime to expand at an accelerating rate. Here's the mind-blowing implication. Given enough time, dark energy will push all the galaxies beyond our cosmic horizon, beyond the distance from which light can ever reach us. In 1 trillion years, intelligent beings in our galaxy will look up at the sky and see nothing but darkness. All evidence of other galaxies will have been stretched away beyond the observable universe. Those future scientists will have no way to discover the Big Bang, no way to know the universe is expanding, no way to detect dark energy. They'll observe a universe that appears static and eternal, containing only their own galaxy surrounded by emptiness. They'll be wrong about the fundamental nature of reality, and they'll have no way to discover their error, because the evidence will have literally left the observable universe. Think about what this means for us. What evidence has already been stretched beyond our cosmic horizon? What fundamental truths about the universe are we unable to discover because the expansion has hidden the evidence? We might be just as cosmically blind as those future scientists, and we'd never know it. But it gets weirder. Remember that 68% of the universe is dark energy? Another 27% is dark matter that doesn't interact with light and can only be detected through its gravitational effects. That means the atoms that make up everything we can see: stars, planets, gas clouds. You account for only 5% of the universe. Everything we've ever seen, touched, or measured directly is a tiny minority of what exists. We live in a universe where 95% of the contents are completely invisible to us, detectable only through gravity. Let me give you an analogy. Imagine you're trying to understand how a car works, but you can only see 5% of the car, maybe just the steering wheel and the tires. You can observe that turning the steering wheel changes the direction the tires point, and you can deduce that there must be some mechanism connecting them, but you can't see the steering column, the rack and pinion, or any of the actual machinery. That's where we are with the universe. We can see matter's effects. We can measure dark matter's gravitational influence. We can detect dark energy's push, but we can't directly observe 95% of what makes the universe work. Dark matter was first proposed by Fritz Zwicky in 1933 when he noticed that galaxies in the Coma cluster were moving too fast to be held together by the gravity of visible matter alone. In the 1970s, Vera Rubin provided compelling evidence by measuring the rotation curves of galaxies. Stars at the outer edges of galaxies orbit just as fast as stars near the center, which should be impossible unless there's a massive halo of invisible matter surrounding each galaxy. Without dark matter, galaxies would fly apart. We know dark matter exists because we can see its gravitational effects. We've mapped dark matter by observing how its gravity bends light from distant galaxies, a phenomenon called gravitational lensing. When light passes near a massive object, space-time curves and the light follows that curvature, creating distorted, magnified images of background galaxies. By studying these distortions, we can map the distribution of dark matter, even though we can't see it directly. And what we found is astonishing. Dark matter forms a cosmic web, with galaxies strung along filaments of dark matter like beads on strings, separated by vast voids containing almost nothing. Here's what should terrify you. Dark matter is probably passing through your body right now. Dark matter particles don't interact with normal matter except through gravity. They pass through Earth, through the walls of your house, through your body, as if you weren't there. Billions of dark matter particles might be streaming through you every second, and you'd never notice. We've built detectors deep underground trying to catch dark matter particles, and so far, we've detected nothing certain. Whatever dark matter is, it's so weakly interacting that even our most sensitive instruments struggle to find it. Now, let's push gravity to even more extreme limits and talk about the boundaries of spacetime itself. General relativity allows for some absolutely bizarre solutions spacetime geometries that are mathematically consistent with Einstein's equations, but seem physically impossible. One of the most famous is the wormhole, technically called an Einstein-Rosen bridge. A wormhole is a tunnel through spacetime, connecting two distant points. Instead of traveling the long way through normal space, you could take a shortcut through the wormhole and emerge instantaneously at a distant location. The mathematics of wormholes is solid. They're legitimate solutions to Einstein's equations. The problem is keeping them open. Every natural wormhole would collapse the instant it formed, unless you could prop it open with something called exotic matter with negative energy density. We've never observed exotic matter in nature, though some quantum effects can produce tiny amounts in laboratory conditions. Without exotic matter, wormholes would snap shut faster than light could pass through them. But here's the kicker. If you could keep a wormhole open, you could build a time machine. Take one end of a wormhole and accelerate it to near light speed, then bring it back. Time dilation means less time passes for the moving end. Now you have a wormhole connecting 2 times enter one end in 2026, exit the other in 2020. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics somehow prevent time machines, possibly because quantum effects would destroy any wormhole the instant it became a time machine. But we don't know for sure. Think of a wormhole like this. Imagine folding a piece of paper so 2 distant points touch, then poking a hole through both layers. That's a 2-dimensional wormhole. Now extend that concept to 3-dimensional space, curved through higher dimensions. The wormhole is the tunnel through that higher dimensional space, connecting points that are far apart in normal space, but adjacent in the higher dimensional structure. General relativity also allows for rotating black holes, called Kerr black holes after Roy Kerr, who found the solution in 1963. Unlike non-rotating black holes, Kerr black holes have 2 event horizons and a region called the ergosphere, where spacetime itself is dragged around the black hole. Inside the ergosphere, you can't stay still even if you fire your rockets at full power. Spacetime is rotating so fast that it carries everything with it. And here's where it gets truly bizarre. The mathematics suggests that if you could pass through both event horizons of a maximally rotating Kerr black hole, you'd emerge not in a singularity, but in another region of spacetime, possibly another universe entirely. This is pure speculation built on mathematical solutions, and most physicists believe you'd be destroyed by tidal forces long before reaching the inner horizon. But the fact that the mathematics allows for such structures should shake your confidence in your understanding of reality. Our best theory of gravity predicts structures that sound like science fiction. Let me hit you with something that's going to change how you think about the universe. Gravity might not be fundamental at all. In the last few decades, some physicists have proposed that gravity is an emergent phenomenon. It arises from deeper physics, the same way temperature arises from molecular motion. Individual molecules don't have temperature. Temperature is a statistical property of many molecules. Similarly, gravity might be a statistical property of quantum entanglement or information. Eric Verlinde proposed in 2010 that gravity is an entropic force. Entropy is a measure of disorder, and the second law of thermodynamics says entropy always increases. Verlinde's idea is that spacetime is made of tiny quantum bits of information, and when matter is present, it changes the distribution of this information in a way that creates what we perceive as gravity. In this view, gravity isn't curving spacetime. Gravity is the thermodynamic pressure created by information wanting to maximize its entropy. This is speculative and controversial, but here's why it matters. If gravity is emergent rather than fundamental, it might help explain why gravity is so much weaker than the other forces. Electromagnetism is roughly 10 times stronger than gravity. A small fridge magnet can overcome the gravitational pull of the entire Earth. Why is gravity so pathetically weak? One answer is that gravity might be diluted across extra dimensions. String theory and M theory suggest the universe has 10 or 11 dimensions, but we only perceive 4. 3 of space, 1 of time. The other dimensions are curled up so small we can't detect them directly. Gravity might propagate through all dimensions, while the other forces are confined to our four-dimensional spacetime. This would make gravity appear much weaker than it really is, like how a sound seems quieter if it's spreading out in 3 dimensions, rather than being confined to a 2-dimensional surface. Think of it like a 2-dimensional creature living on the surface of a balloon. If you push on the balloon, creating a dimple, the 2D creature experiences that as a force within its 2D universe. But the actual cause of the force is 3-dimensional. It's the balloon material, curving through the 3rd dimension. Similarly, gravity might be the effect of spacetime curving through higher dimensions we can't directly perceive. Here's your second major mind-blown moment. If extra dimensions exist, microscopic black holes could be created in particle accelerators. When the Large Hadron Collider smashes protons together at nearly the speed of light, it concentrates enormous energy in a tiny space. If extra dimensions exist and gravity propagates through them, gravity becomes much stronger at small scales, and that energy might be enough to curve spacetime into a microscopic black hole. These micro black holes would evaporate instantly through Hawking radiation. They'd pose no danger, but their detection would prove extra dimensions exist. So far, we haven't seen them, which puts constraints on the size and number of extra dimensions. But the fact that we're even looking for microscopic black holes at CERN should give you a sense of how strange gravity becomes when we probe its limits. Let's talk about Hawking radiation, because it reveals one of the deepest conflicts in modern physics. In 1974, Stephen Hawking showed that black holes aren't entirely black. Quantum mechanics allows for particle-antiparticle pairs to spontaneously appear near the event horizon. Normally, these pairs immediately annihilate each other. But near a black hole, one particle can fall into the black hole while the other escapes. From an outside perspective, it looks like the black hole is emitting radiation. Over immense timescales, this radiation carries away the black hole's mass and energy, and eventually, the black hole evaporates completely. Here's the problem. The radiation appears to be random thermal radiation, carrying no information about what fell into the black hole. But quantum mechanics says information cannot be destroyed. It's a fundamental principle. So what happens to the information about everything that fell into the black hole? Does it disappear, violating quantum mechanics? Does it somehow get encoded in the Hawking radiation through some mechanism we don't understand? This is the black hole information paradox, and it's one of the deepest unsolved problems in theoretical physics. The paradox reveals a fundamental conflict between general relativity and quantum mechanics. General relativity says black holes destroy information. Quantum mechanics says information cannot be destroyed. Both theories can't be completely correct, which means we need a deeper theory that unifies them. A theory of quantum gravity. String theory attempts to be that theory by proposing that all particles are actually tiny vibrating strings, and gravity is carried by a particular vibration pattern called a graviton. Loop quantum gravity attempts it by suggesting spacetime itself is quantized, made of discrete chunks rather than being continuous. Both approaches make progress on different problems, but neither is complete, and we have no experimental evidence to distinguish between them. Here's what keeps physicists up at night. Quantum mechanics and general relativity are the two most successful theories in the history of science. Quantum mechanics has been tested to absurd precision in particle physics. General relativity has been confirmed in everything from GPS satellites to gravitational waves. Yet they contradict each other at a fundamental level. One of them or both must be approximations of a deeper truth we haven't discovered yet. Think of it like this. Imagine you have two maps of the same city. One map is perfect for the downtown area, but completely wrong about the suburbs. The other map is perfect for the suburbs, but nonsense downtown. Both maps are useful in their domains, but they contradict each other in the overlap region. You know there must be a true map that correctly describes both regions, but you haven't found it yet. That's where we are with quantum mechanics and general relativity. We're about 90 minutes in now, and if you need a break, take one. Seriously, go get some water, stretch, let your brain rest for a minute. When you come back, we're going to talk about how all of this directly affects you, how gravity shapes your personal experience of reality in ways you've never considered. Before we continue, drop a comment telling me which concept so far has blown your mind the most, and make sure you're subscribed, because the second half of this video is going to get even more intense. Now let's bring this home and talk about how gravity affects your daily life in ways you never realized. You know what's weird? You're getting shorter right now. Throughout the day, gravity compresses your spine, and you can lose up to an inch of height between waking and sleeping. When you lie down at night, your spine decompresses, and you regain that height. Astronauts in zero gravity grow up to 2 inches taller because there's no gravitational compression. When they return to Earth, they shrink back down as gravity reasserts its grip on their bodies. But here's something more profound. Gravity is actively shaping your body right now at the cellular level. Your bones are constantly being rebuilt. Cells called osteoclasts break down old bone, and cells called osteoblasts build new bone. This process is regulated partly by mechanical stress. When you put weight on your bones, it stimulates osteoblasts to build more bone. In zero gravity, astronauts lose bone density at about 1 to 2% per month because their bones aren't experiencing the mechanical stress they evolved for. Gravity literally sculpted your skeleton into its current shape through millions of years of evolution. Your cardiovascular system is designed around gravity. Your heart has to pump blood upward against gravity to reach your brain. That's why you have valves in your veins to prevent blood from flowing backward when gravity pulls it down. Stand up too quickly, and you might feel dizzy because gravity pulls blood away from your brain faster than your cardiovascular system can compensate. In zero gravity, astronauts' hearts become slightly weaker because they don't need to pump against gravity, and fluid shifts toward their heads, making their faces puffy. Think about this. Every movement you make is a negotiation with gravity. When you reach for a cup, your brain automatically calculates the trajectory to compensate for gravity pulling your arm down. When you throw a ball, your unconscious mind solves differential equations to predict the parabolic arc. You're a gravity computation machine, and you don't even realize it because evolution has made the calculations automatic. Here's something that will change how you think about your weight. You weigh less at the equator than at the poles. Earth is rotating, and that rotation creates a centrifugal effect that slightly counteracts gravity. At the equator, where Earth's rotational speed is highest, you weigh about 0.5% less than you would at the North Pole. Additionally, Earth is not a perfect sphere. It bulges at the equator due to rotation. This means you're farther from Earth's center at the equator, which also reduces gravity slightly. If you weigh 150 pounds at the North Pole, you'd weigh about 149.25 pounds at the equator. Mountains also affect gravity. The mass of a mountain creates a slight gravitational attraction, pulling you toward the mountain. Surveyors have to account for this when making precise measurements. Massive geological formations can deflect a plumb line by small but measurable amounts. This was actually one of the early tests of Newton's gravity. Scientists measured how much the Andes Mountains deflected a pendulum and used that to estimate Earth's mass and density. Now here's where it gets personal and existential. Gravity is fundamentally connected to your experience of time, and most people never realize this. Time moves slower for you than for someone on a mountain. This isn't philosophy, it's measurable physics. In 2010, researchers at NIST, National Institute of Standards and Technology, used atomic clocks to measure time dilation over a height difference of just 1 foot. They found that a clock 1 foot higher ticked faster than a clock on the ground. The difference is tiny, about 90 billionths of a second per day, but it's real. Your head is aging slightly faster than your feet because your head is farther from Earth's center. Think about what this means. Your subjective experience of time is affected by gravity. If you spend your life on the ground floor versus the top floor of a skyscraper, you will age very slightly differently. The person on the top floor will age perhaps a few millionths of a second more over a lifetime. It's negligible, but it demonstrates that your personal timeline is not universal. It's affected by your location in Earth's gravitational field. Here's the mind-bending part. Because time moves slower in stronger gravity, your feet are slightly younger than your head. Every part of your body is experiencing time at a slightly different rate depending on its distance from Earth's center. You're not moving through time as a unified object. You're a distributed structure with different parts, experiencing slightly different time flows. Let me give you an analogy. Imagine a marching band where people in the front walk slightly slower than people in the back. After marching for a while, the formation gets stretched and distorted. That's what gravity does to time. Your feet are in slightly stronger gravity than your head, so they're marching through time slightly slower, and over the course of your life, they've experienced infinitesimally less time. Now, the really disturbing thought. If you're experiencing time dilation right now due to Earth's gravity, what about the universe's expansion? Dark energy is accelerating the expansion of space, which means the universe's geometry is constantly changing. Does this affect time? The answer is yes. Observers in different parts of an expanding universe can disagree about simultaneity. Events that appear simultaneous to one observer might appear sequential to another. The universe doesn't have a universal now. This destroys the intuitive notion of the present moment. You think there's a present moment happening right now throughout the entire universe, that somewhere on Alpha Centauri, there's an exact present instant corresponding to this exact present instant on Earth. But that's not how space-time works. Due to relativity and the expansion of the universe, there is no absolute present. Different observers can legitimately disagree about whether two distant events happened at the same time. Think about what this means for your existence. The present moment is not a universal slice through time. It's a local, observer-dependent phenomenon. Your now is not the same as someone else's now if you're in different gravitational fields or moving at different velocities. The past, present, and future are not absolute categories. They're relative to the observer. Here's your third major mind-blown moment. According to some interpretations of relativity, all of time exists simultaneously. Past, present, and future are all equally real. They're just different regions of space-time. You think you're moving through time from past to future, but from a four-dimensional perspective, your entire life, from birth to death, exists as a complete, unchanging structure in space-time. You're not moving through time. Your consciousness is experiencing different slices of an unchanging four-dimensional you. This is called the block universe interpretation, and it suggests that the future is already determined, not because some external force is controlling it, but because the future already exists as part of the space-time structure. If this is true, then free will is an illusion. Every choice you think you're making was already encoded in the structure of space-time at the moment of the Big Bang. But here's the counter-argument. Quantum mechanics introduces genuine randomness into the universe. The outcome of quantum events isn't determined until they're measured. This could preserve some form of free will, or at least introduce genuine unpredictability into the universe's evolution. We don't know how to reconcile quantum mechanics with the block universe, and that's one of the deepest problems in physics. Let me bring this back to something tangible. Gravity affects your health in ways you never considered. Your immune system functions differently in zero gravity. White blood cells, the cells that fight infection, use gravity-sensitive mechanisms to detect and move toward pathogens. In zero gravity, this process is disrupted, and astronauts' immune systems become less effective. They're more susceptible to infections in space than on Earth. Your sense of balance comes from tiny calcium crystals in your inner ear called otoliths. Gravity pulls on these crystals, and your brain uses that information to determine which way is up. In zero gravity, the otoliths float freely, sending confused signals to your brain. This is one reason astronauts often feel nauseous when they first reach orbit. Their balance system is telling them they're falling, but they never hit the ground. Sleep is affected by gravity. When you lie down, fluid redistributes in your body, and your brain receives less pressure from gravity. This affects your circadian rhythm, your natural sleep-wake cycle. Astronauts often struggle to maintain normal sleep patterns because the cues their bodies evolved to use, like gravity's effects on fluid distribution, are absent. Here's something really weird. Muscles need gravity to develop properly. Babies in the womb are experiencing microgravity. They're floating in amniotic fluid, but they're still in Earth's gravitational field, which affects how their mother's body positions them, how blood flows to them, and how their tissues develop. If you tried to gestate a baby in true zero gravity, we don't know if development would proceed normally. Some animal studies suggested wooden gravity might be necessary for proper organ and tissue formation. Think about the implications. Life as we know it evolved under a specific gravitational acceleration, 9.8 meters per second squared on Earth's surface. Every biological process, from cellular division to organ formation to muscle contraction, was optimized for this specific level of gravity. If you were born and raised on Mars, which has about 38% of Earth's gravity, would your body develop the same way? Probably not. You'd likely be taller, your bones would be less dense, your muscles weaker, your heart smaller. You'd be adapted to Martian gravity, but you might never be able to visit Earth without suffering under gravity 2.6 times stronger than what your body was built for. Now let's talk about something that should fundamentally shift your worldview: the anthropic principle and gravity's role in making the universe habitable. The strength of gravity in our universe is precisely tuned to allow for complex structures like stars, planets, and life. If gravity were slightly stronger, stars would burn out too quickly for life to evolve. If it were slightly weaker, stars wouldn't form at all, matter would just disperse into a cold, dark void. The ratio of gravity's strength to the other fundamental forces has to fall within a narrow range for the universe to produce anything interesting. This is deeply unsettling because it suggests one of three possibilities. 1. We're incredibly lucky. 2. The laws of physics were deliberately set to allow for life. 3. There are countless universes with different laws of physics, and we necessarily find ourselves in one where the laws permit our existence. Option 3 is the multiverse hypothesis, the idea that our universe is just one bubble in an infinite foam of universes, each with different physical constants and laws. In most of those universes, conditions are hostile to life. But in the vast ensemble, some universes like ours happen to have the right conditions. We exist in this universe not because it's special, but because we couldn't exist in the others. Think about what this means. Gravity's strength isn't a fundamental necessity. It's an accident of our particular universe's initial conditions. In another universe, gravity might be 1,000,000 times stronger, or effectively non-existent. And if the multiverse hypothesis is correct, those universes actually exist, somewhere beyond our cosmic horizon, completely inaccessible to us. Here's the disturbing corollary. If the multiverse is real, everything that can happen does happen somewhere. Every possible decision you could make, you do make in some parallel universe. Every possible history plays out somewhere in the infinite ensemble. This doesn't just apply to your personal choices, it applies to the fundamental structure of reality. Somewhere, there's a universe where gravity works completely differently, where matter doesn't even exist as we know it, where the very concept of space and time might be foreign. But we can't test this. The multiverse hypothesis might be fundamentally untestable because, by definition, other universes are beyond our cosmic horizon. Some scientists argue this makes the multiverse hypothesis unscientific. It's not falsifiable. Others argue it's a logical consequence of well-established theories like quantum mechanics and cosmic inflation, and we should take it seriously, even if we can't test it directly. Let me hit you with something that ties this all together. the holographic principle. In the 1990s, Gerard 't Hooft and Leonard Susskind proposed that all the information contained in a volume of space can be encoded on the boundary of that volume like a hologram. A hologram is a two-dimensional surface that contains all the information needed to reconstruct a three-dimensional image. The holographic principle suggests our three-dimensional universe might be a hologram. All the information about what's happening in this volume of space is encoded on a two-dimensional surface at the universe's boundary. This came from studying black holes. Stephen Hawking and Jacob Bekenstein showed that a black hole's entropy, the amount of information it contains, is proportional to its surface area, not its volume. This is weird because you'd expect the information content to scale with volume, not surface area. The holographic principle generalizes this. Maybe the universe itself works the same way, with all information encoded on its boundary. Here's the mind-bending implication. You might be a two-dimensional pattern projected into three-dimensional space. The you that feels three-dimensional might be a holographic projection of information encoded on a distant, two-dimensional surface. Your entire life, all your experiences, every thought you've ever had might all be a shadow of deeper two-dimensional information. This sounds like science fiction, but it's grounded in serious physics. The ADC-FT correspondence, discovered by Juan Maldacena in 1997, is a precise mathematical realization of the holographic principle. It shows that a quantum field theory in a flat space can be exactly equivalent to a gravitational theory in a space with one additional dimension. This suggests that gravity itself might be holographic, an emergent phenomenon arising from more fundamental quantum information on a lower dimensional boundary. Think about what this means for the nature of reality. The universe might have fewer dimensions than you perceive. Your three-dimensional experience might be an illusion created by information processing on a two-dimensional surface. This would mean that space-time, and by extension, gravity, is not fundamental. It's an emergent holographic projection. We're approaching the 2-hour mark now, and I want to make sure you're still with me. Take a second to like this video if it's changing how you see reality, and drop a comment with your biggest question. What we're building toward is a complete reconceptualization of your place in the universe, and I promise the payoff is coming. Let's talk about the future. What happens to gravity as the universe ages? Current observations suggest the universe will expand forever, accelerating due to dark energy. As space expands, galaxies that are currently visible will eventually move beyond our cosmic horizon. In about 100 billion years, almost every galaxy, except those in our local gravitational cluster, will have been stretched beyond the observable universe. Future observers will see a universe containing only their local galaxy group surrounded by darkness. But it gets worse. Stars have finite lifetimes. The sun will burn out in about 5 billion years. Larger stars burn out faster. Smaller stars burn out slower. The smallest red dwarf stars might last 1 trillion years. But eventually, all stars will exhaust their fuel. The universe will enter what's called the degenerate era, where the only objects are dead stellar remnants, white dwarfs, neutron stars, and black holes. Over immense timescales, 10 to 10 years, these remnants will themselves decay or be consumed by black holes. Gravity will drive everything into black holes eventually. And then what? The black holes evaporate through Hawking radiation. The largest black holes, the supermassive black holes at galaxy centers, will take about 10 years to evaporate. That's a 1 followed by 100 zeros. For comparison, the current age of the universe is less than 10 years. After the black holes evaporate, the universe enters the dark era nothing but increasingly dilute radiation spreading across an exponentially expanding space. Temperature approaches absolute zero. No structure, no complexity, no life. Just photons and occasional particles separated by voids larger than our current observable universe, slowly drifting apart forever as dark energy continues to push space apart. This is the heat death of the universe. the ultimate victory of entropy and the ultimate defeat of gravity. Gravity tries to pull things together, to create structure and complexity. But dark energy pushes things apart, and it's stronger. In the end, dark energy wins, and the universe becomes a cold, dark, empty void expanding forever. Here's what's profound about this. Gravity is what makes the universe interesting. Gravity creates stars, planets, galaxies. It creates structure from chaos. Without gravity, the universe would just be a uniform soup of particles expanding forever with no complexity, no structure, no possibility of life. Gravity fights against entropy, creating islands of order in a sea of chaos. But ultimately, gravity loses. Entropy wins. The universe ends in maximum disorder. Unless, and this is speculative, there's something we don't understand about dark energy. If dark energy is not constant, but changing over time, the ultimate fate of the universe could be different. Some models suggest dark energy could strengthen, leading to a big rip, where the accelerating expansion eventually tears apart galaxies, stars, planets, atoms, and even spacetime itself. Other models suggest dark energy could weaken or reverse, potentially leading to a big crunch where gravity finally wins and the universe collapses back into a singularity. We don't know. We can't predict the ultimate fate of the universe because we don't understand dark energy. We're extrapolating based on current observations, but we could be completely wrong about what happens in the deep future. Think about the existential weight of this. If the heat-death scenario is correct, everything that has ever happened or ever will happen, all of human history, all of Earth's species, all the art and music and love and suffering, will eventually be erased as the universe fades into cold, dark silence. The universe will eventually forget that we ever existed. But here's a different perspective. The fact that we exist at all, in this brief cosmic moment where stars shine and planets harbor life, is extraordinary. We live in the universe's youth, in an era where gravity has created enough structure for complexity to arise, but hasn't yet surrendered to entropy. We're part of the universe's brief flowering, and that makes our existence precious. Let me shift gears and talk about something that brings this back to human scale. What does all this mean for you personally? You are a temporary reversal of entropy, created and sustained by gravity. Your body is an island of order in a universe trending toward disorder. You maintain your structure by constantly consuming energy food and radiating waste heat. You're a localized decrease in entropy, and that's only possible because Earth receives energy from the sun, which is powered by gravity, crushing hydrogen atoms together until they fuse. Gravity created the sun. Gravity keeps Earth in orbit. Gravity pulls nutrients through your body. Gravity literally shapes your cells and organs. You are a gravitational phenomenon. You're what happens when gravity creates enough structure for matter to become self-aware. Here's the profound part. You're made of stardust, and that's not just a poetic metaphor, it's literal fact. The heavy elements in your body, carbon, nitrogen, oxygen, calcium, iron, were forged in the cores of stars that exploded billions of years ago. Those stars formed through gravitational collapse, fused light elements into heavy ones through gravitationally powered fusion, and then exploded, scattering those elements into space. Gravity then gathered that enriched material into new stars and planets, eventually forming Earth, and billions of years later, you. Every atom in your body is 13.8 billion years old, and many of them have been through multiple stellar furnaces. The calcium in your bones was forged in a supernova explosion. The iron in your blood was created in the collapsing core of a massive star. You're literally made from stellar corpses, assembled by gravity into a configuration that can think and feel and wonder about its own existence. Think about what this means. You're not separate from the universe. You're a way the universe has organized itself to experience itself. Your consciousness is an emergent property of matter that has been shaped by gravity over billions of years. When you look up at the stars, you're looking at your ancestors, not your genetic ancestors, but your atomic ancestors. The atoms in your body came from stars. Here's your fourth major mind-blown moment. Given the holographic principle and the block universe interpretation, your entire life, every moment from birth to death, already exists as a complete structure in spacetime. Your experience of moving through time is like reading a book. The entire book exists at once, but your consciousness experiences it one page at a time. The you reading this right now is just one page in a book that's already been written. This raises profound questions about identity and continuity. Are you the same person you were 10 years ago? Physically, almost every atom in your body has been replaced since then. The only continuity is the pattern, the specific arrangement of matter and energy that constitutes you. And if the block universe is correct, that pattern exists in its entirety across all of time. The 10-year-ago version of you and the current version of you both exist. They're just different cross-sections of your complete four-dimensional self. Now, let's tackle one of the biggest questions. Does consciousness affect gravity? Standard physics says no consciousness is an emergent property of matter, and it doesn't directly affect space-time curvature. But there's a weird corner of quantum mechanics that suggests something stranger might be happening. The measurement problem in quantum mechanics asks, what causes the wave function to collapse from multiple possibilities into one definite outcome? Some interpretations suggest that conscious observation plays a role. If consciousness affects quantum mechanics, and quantum mechanics underlies all of reality, then consciousness might indirectly affect everything, including gravity. This is highly speculative, and most physicists think consciousness is just an emergent property with no special role in physics. But the measurement problem remains unsolved, and we can't completely rule out the possibility that consciousness has some role to play in the fundamental structure of reality. Here's a thought experiment. Imagine you're in a quantum superposition, existing in multiple states simultaneously until observed. Your mass in each state would curve space-time differently. When the superposition collapses to a single state, the gravitational field would change. If consciousness causes collapse, then consciousness is indirectly affecting gravity. This is wildly speculative, but it's not completely ruled out by current physics. Think about what this could mean. If consciousness affects reality at a quantum level, then you're not just a passive observer of the universe, you're an active participant in shaping it. Every observation you make, every measurement you take, every moment of conscious awareness might be collapsing quantum wave functions and determining which version of reality becomes actual. This ties into the anthropic principle. We observe a universe compatible with our existence, not just because we couldn't exist in other universes, but possibly because our observation is actively selecting this universe from among many possibilities. The act of conscious observation might be what makes the universe definite rather than a fuzzy superposition. Again, this is speculative, and most physicists are skeptical. But the fact that we can't rule it out should give you a sense of how much we still don't understand about consciousness, quantum mechanics, and gravity. Let me bring this toward a conclusion by talking about the biggest open questions in gravity research. First, what is quantum gravity? We know gravity works at large scales through Einstein's general relativity, and we know quantum mechanics works at small scales, but we don't have a theory that unifies them. At the Planck scale, about 10 meters and 10 seconds, both quantum effects and gravitational effects become important, and our current theories break down. We don't know what happens in that regime. String theory and loop quantum gravity are the leading candidates, but we have no experimental evidence for either. The energy scales required to test quantum gravity directly are beyond anything we can achieve with current technology. We'd need a particle accelerator the size of the solar system to probe the Planck scale directly. Second, what is dark matter? We've detected its gravitational effects, we've mapped its distribution, but we don't know what it's made of. Is it WIMPs? Weakly interacting massive particles? Axions? Primordial black holes? Something completely unexpected? Solving the dark matter mystery could revolutionize physics. Third, what is dark energy? We know it's causing the universe's expansion to accelerate, but we don't know what it is. Is it a cosmological constant? A dynamic field called quintessence? A sign that general relativity breaks down at cosmological scales? Understanding dark energy would tell us the ultimate fate of the universe. Fourth, what happened at the Big Bang singularity? Our equations break down there, just like they break down at black hole singularities. We need quantum gravity to describe the very beginning of the universe. Did time really begin at the Big Bang? Or was there something before? We don't know. Fifth, are there gravitons? If gravity is quantized like the other forces, there should be a particle that mediates gravity, the graviton. But gravitons would interact so weakly with matter that we might never be able to detect them directly. Does gravity even quantize the same way the other forces do? Or is it fundamentally different? Sixth, does gravity modify quantum mechanics? Or does quantum mechanics modify gravity? This is an active area of research. Some theories suggest that gravity causes wave function collapse. Others suggest quantum effects modify general relativity at small scales. We're still figuring out how these two pillars of physics fit together. Here's what you need to understand. Despite all our knowledge, gravity remains deeply mysterious. We can describe how it works with exquisite mathematical precision. We can use it to predict planetary orbits, design GPS satellites, and detect gravitational waves, but we don't know what it fundamentally is. We don't know why mass curves spacetime. We don't know how to reconcile it with quantum mechanics. We don't know what happens at singularities. Think about the audacity of human knowledge. We've measured gravitational waves from black holes colliding 1 billion light-years away. We've photographed the shadow of a black hole. We've detected time dilation over a height difference of 1 foot. We've mapped the distribution of dark matter across the universe. We've traced cosmic expansion back to fractions of a second after the Big Bang, but we still can't tell you what gravity fundamentally is. This should be humbling and exhilarating. Humbling because it shows how much we don't know. Exhilarating because it means there are still profound discoveries waiting to be made. Now, let me tie everything together and show you why this matters for how you see yourself and your place in the universe. You are a pattern of matter sustained by energy flows, shaped by gravity over billions of years of cosmic evolution. You're made of atoms forged in stars, assembled on a planet created by gravitational collapse, held to that planet by the curvature of spacetime, experiencing time at a rate determined by your position in Earth's gravitational field. Your existence is temporary, an infinitesimal moment in cosmic history. But it's also extraordinary. You're one of the few structures in the universe complex enough to understand gravity, to measure it, to manipulate its equations, and predict its effects. You're a way the universe has organized itself to study itself. Gravity connects you to everything. The same force keeping you on Earth is holding galaxies together, curving light from distant quasars, creating the conditions for stars to form and life to emerge. You're not separate from the cosmic dance, you're part of it. Every breath you take, every heartbeat, every movement is orchestrated by gravity, acting on matter across scales from your body to the observable universe. The block universe interpretation suggests your entire life exists eternally as a structure in spacetime. The past isn't gone, and the future isn't undetermined. They're just different regions of a four-dimensional reality where past, present, and future are equally real. Your consciousness experiences time sequentially, but from a higher dimensional perspective, you exist in your entirety, from birth to death, as a complete, unchanging pattern. The holographic principle suggests you might be a projection of information encoded on a distant boundary. Your three-dimensional experience might be an illusion, a shadow of deeper two-dimensional information. This doesn't make your experience less real. It just means reality has more layers than you perceive. The anthropic principle suggests you exist in this universe, with this particular strength of gravity, because universes with different gravitational constants couldn't produce observers like you. You're not a random accident. You're a necessary consequence of the physical laws that govern your universe. In the vast multiverse of all possible universes, you exist in this one because this is the kind of universe that produces beings who can ask why they exist. Here's what I want you to take away from this. You matter, not in a cosmic sense. The universe doesn't care about you. Stars will continue to burn. Galaxies will continue to collide. Dark energy will continue to push space apart, completely indifferent to your existence. But you matter in the sense that you're extraordinary. Against overwhelming odds, matter has organized itself into a configuration that can think, feel, love, wonder, and understand the very forces that created it. Gravity created the conditions for your existence. Gravity assembled the atoms in your body. Gravity shapes your daily experience. And now, through your understanding of gravity, you're participating in the universe's self-awareness. You're one of the tiny number of structures in all of space-time that can comprehend what gravity is, how it works, and what it means. The universe is vast beyond comprehension. There are more stars than grains of sand on all of Earth's beaches. Most of space is empty void. Most of time is the far future, when the universe will be cold and dark. But you exist here and now, in this brief cosmic moment when stars shine and life flourishes. You're part of the universe's flowering, its brief moment of complexity and beauty before entropy wins and everything fades. Don't waste it. Don't take it for granted. You're literally made of stardust, held together by fundamental forces, experiencing consciousness through mechanisms we barely understand, existing in a universe fine-tuned to allow your existence. That's not a metaphor. It's physics. When you look up at the night sky, you're seeing your history. Those stars created the atoms in your body. That darkness between the stars is space being stretched by dark energy. Those distant galaxies are being carried away by the expansion of space-time. You're connected to all of it through gravity, the curvature of space-time that links everything to everything else. And here's the final mind-blown moment. You are the universe experiencing itself. Your consciousness is a localized expression of cosmic self-awareness. When you think about gravity, when you wonder about black holes and dark energy and the fate of the cosmos, you're not an external observer studying an object. You're an internal part of the system studying itself. The universe is using your brain to understand its own structure. This is profound. Consciousness isn't separate from physical reality. It's an emergent property of it. Your thoughts about gravity are themselves products of gravity, acting on matter over billions of years to create brains capable of abstract thought. The equations you can understand, the wonder you can feel, the awe you experience contemplating the cosmos, all of it is the universe contemplating itself through you. You have about 100 billion neurons in your brain. The observable universe has about 100 billion galaxies. That's not a coincidence. It's a reminder that you contain multitudes. Your internal mental universe is as complex as the cosmic structure you're trying to understand. You're a microcosm reflecting the macrocosm. So what do you do with this knowledge? How does understanding gravity change how you live? First, it should give you perspective. Your problems, your worries, your anxieties, they're real and valid, but they're also infinitesimally small in cosmic terms. The universe is 13.8 billion years old and 93 billion light years across. You'll live maybe 100 years on a planet that's a tiny speck orbiting an average star in an unremarkable galaxy. This could be depressing, but it's actually liberating. It means you're free. Free to define your own meaning, to create your own purpose, to decide what matters to you. Second, it should inspire wonder. You live in an era where we can detect gravitational waves, photograph black holes, measure time dilation in tabletop experiments, and trace cosmic history back to fractions of a second after the Big Bang. You have access to, knowledge that was literally impossible for humans to obtain until very recently. Use it, learn, wonder, be amazed. Third, it should foster connection. Gravity connects everything. You're part of a cosmic web of cause and effect, stretching back to the Big Bang and forward to the heat death of the universe. You're connected to everyone and everything through the fundamental forces of nature. This isn't mysticism, it's physics. Act like it. Recognize your connection to the larger whole. Fourth, it should encourage humility. Despite all our knowledge, we still don't understand the fundamental nature of gravity. We don't know what dark matter is. We don't know what dark energy is. We don't know how to reconcile quantum mechanics with general relativity. We don't know what consciousness is, or whether it plays any special role in physics. We know a lot, but we don't know everything. And the more we learn, the more questions we discover. Fifth, it should motivate curiosity. The open questions in gravity research are some of the most profound in all of science. What is quantum gravity? What happens at singularities? Is the holographic principle correct? Does the multiverse exist? These questions might be answered in your lifetime, or you might be part of answering them. The frontier of knowledge is still wide open. Finally, it should give you a sense of your place in the cosmic story. You're not separate from the universe. You're a chapter in its unfolding narrative. Your life is a brief episode in cosmic history, but it's your episode. Make it meaningful. Make it count. Before we wrap up, I want to address one more thing: the emotional weight of these ideas. Understanding that the universe is vast, ancient, and largely indifferent to your existence can be overwhelming. Understanding that your free will might be an illusion, that your entire life exists as an unchanging structure in spacetime, that consciousness might be nothing more than an emergent property of matter. These ideas can be existentially challenging. But here's another way to look at it. Even if your choices are determined by the laws of physics, they're still your choices. Even if your life is a predetermined path through spacetime, you still have to experience it moment by moment, and those experiences are real. Even if consciousness is emergent, it's still consciousness. You still feel, think, love, suffer, and experience wonder. The fact that everything can be reduced to particles following physical laws doesn't make it less meaningful. It makes it more amazing. The fact that unconscious matter, following simple rules, can organize itself into structures complex enough to experience joy, love, curiosity, and awe is extraordinary. You're proof that the universe, left to its own devices, spontaneously generates meaning. Don't let the vastness of the cosmos diminish your sense of significance. You're significant because you're part of the universe becoming aware of itself. You're significant because you can understand these ideas. You're significant because you can feel wonder at the beauty of physical law. Gravity doesn't care about you, but you can care about gravity. You can study it, understand it, marvel at it, and share that understanding with others. That's your power as a conscious being. You can create meaning in a universe that doesn't inherently have any. So here's my final message. Go forth with a sense of wonder. Look at falling objects differently now. Recognize that they're following geodesics through curved spacetime. Feel your weight differently. It's not gravity pulling you down. It's the ground accelerating upward into you. Look at the stars and recognize their gravitational furnaces, powered by the same force that keeps your feet on the ground. You've spent 3.5 hours learning about how gravity works around the universe. You've traveled from Newton's apple to black holes, from gravitational waves to dark energy, from quantum foam to the heat death of the cosmos. You understand now that gravity isn't a force, it's the curvature of spacetime itself. You understand that your experience of time is affected by gravity. You understand that you're made of stardust, shaped by gravity over billions of years. Most importantly, you understand that you're not an observer of the universe, you're a participant in it. You're part of the cosmic dance, connected to everything through the fundamental forces of nature. Your existence is temporary but extraordinary, meaningless in cosmic terms, but full of meaning in human terms. Thank you for taking this journey with me. If this video changed how you see reality, hit that like button and subscribe for more deep dives into the fundamental nature of existence. Drop a comment telling me what blew your mind the most, and share this with someone who needs a cosmic perspective on their life. Remember, you're a way the universe has organized itself to study itself. Don't waste that opportunity. Keep learning, keep wondering, and keep looking up at the stars, recognizing that you're looking at your origins. The universe is vast, strange, and beautiful, and you're part of it. That makes you vast, strange, and beautiful too. Now go out there and appreciate gravity. It's literally what holds everything together, including you.